Our speaker today is Kyoto Yoshino, who is a doctoral student working under Akihiro Minamasa at Tohoku University. Mr. Yoshino works on problems in equiangular lines and graph algorithms. Today, he will tell us about the Lemon-Seidel conjecture for base size 5. Take it away, Kyoto.
Thank you for introduction. Thank you for giving me this opportunity. I'm supported by JSPS. This talk is based on this archive paper. The title is the Lemon-Seidel conjecture for base size 5. This is the outline of my talk. First, I describe well-known results on equiangular lines and the so-called Lemon-Seidel conjecture. After that, I introduce Seidel matrices and graphs corresponding to equiangular lines. Additionally, I explain the pillar method. It's our main tool. And I describe the proof of the case for base size 6. Now, Lemons and Seidel gave this in 1973. After that, I explain my result and its proof. Also, as written in the abstract, Ring and Yu claimed to prove the Lemon-Seidel conjecture for base size 5. Since there is a gap in their argument, I give a counterexample. The strategy of my proof is different from theirs. Lines in Euclidean space are equiangular if any pair of lines forms the same angle. Now, in this figure, 3 lines are equiangular, and the common angle is pi/3. I write n alpha d for the maximum value of the number of equiangular lines with common angle cos alpha in dimension d. And I write n d for the maximum value of the number of equiangular lines in dimension d. The problem of determining n d and n alpha d dates back to the result in 1945. First, I present some general results. This upper bound is the so-called absolute bound, and the lower bound was given by Greaves, Professor Greaves, Professor Curran, and Professor Minamasa, and Professor Source. Also, in dimensions at most 43, the values of bounds on ND are known. Recently, Greaves and others have improved the bound of LD in dimension 17 and 18 in the spectral method. Next, in this slide, we focus on the results for a fixed angle. Lemons and Seidel proves that if a set of n equiangular lines with common angle cos alpha in dimension d satisfies n is greater than 2d, then 1 over alpha is an odd integer. In addition, they proved that if d is less than 1 over the square of alpha, then n alpha d is at the most this one. And recently, Jiang and others proved this. So this holds in high dimensions. And next, the values of n 1/3 d are known. Revens I decided proved this in the pyramid method. In dimension 5, this value takes 10. If d equals 6, 16. If d equals 7, 28. And recently, Professor Tsao and Professor Kuren, Professor Munemasa, and I classified the maximal equiangular lines with common angle arc cos 1/3 by using root lattices. So this is more precise results. This is the Riemann-Sizer conjecture. If d is at least 23, then n 1/5 d is at most 276 over 3d minus 3 over 2. We need to show it for base size 3, 4, 5, and 6.
Hey, can I stop to ask a question quick? What does it mean base size?
Actually, I will define that.
Okay, I'm sorry.
Okay.
Maybe I got ahead.
Okay, sorry. In 1983, Riemann and Sider proved it for base size 6, and 2020, Ring and Yu proved it for base size 6 with a computer, and claimed to prove it for base size 5. However, there is a gap. Professor Tsao, Professor Guren, and Professor Lin and Professor Yu proved it for base size 3 and 4. So I proved it for base size 5. And the main tool is pyramid method. So, I proved this theorem. A set of n equiangular lines with common angle cos 1/5 with base size 5 in dimension d satisfies n is at most of 276 or 40 plus 10/3. When these at least 30, then this is greater than this. And when these 30, this is at the most 276. So, okay. Next, I introduce Sider matrices and graphs and base size. Zeider matrices were introduced in connection with equiangular lines. Zeider matrix is a symmetric matrix with zero diagonal and all of diagonal entries +1 or -1. This is an example. Two Zeider matrices S and S prime are switching equivalent if there exists a signed permutation matrix P such that S and S prime satisfies this. Next, we represent Zeider matrices by graphs. For graph gamma, I define S gamma as J minus I minus 2 times A gamma. Here, J is the all-one matrix, and A gamma is the adjacency matrix. Eigenvalue S gamma is called Zeider eigenvalue of gamma. If S gamma and S delta are switching equivalent, then two graphs gamma and delta are switching equivalent. This is our example. In this figure, two graphs gamma and delta are switching equivalent. So by fixing a partition and switching the edges between them, so I delete this edge, and add these edges. We can get from one to the other. Okay. A bracket gamma is a set of graphs switching equivalent to gamma. And let omega gamma be the clique number of gamma. And let omega bracket gamma is the maximum value of omega delta, where delta is a member of bracket gamma. Okay. Next, I explain relation between Zeider matrices and equiangular lines. Let S be a Zeider matrix with smallest eigenvalue at least minus lambda. Then there exist vectors U1 over UN in Euclidean space such that I plus 1 over lambda times S equals the graph matrix of U1 over UN. Then the lines spanned by U1 over UN form the set of equiangular lines with common angle arc cos 1 over lambda. Conversely, S can be recovered from these lines after switching. For example, if I take U as in this figure, then we obtain this Zeider matrix. If we fix U as in this figure, then we get this Seidel matrix. And the corresponding graphs is triangle and this one. The relationship summarized in this table. So now you want to consider a set of rectangular lines with common angle arc cos 1/3. So we consider the graphs with smallest Seidel eigenvalue at least -5. Next, I define pillars. The best set of a set E of rectangular lines is the maximum value of group numbers of graphs induced by E. This is an example. This set of rectangular lines induces two graphs. The maximum, click number is 3. The click number of this graph is 1. So the base size is 3. And next, I fix graph H and take maximum click B and a subset to U of B. Then a pillar BU is the induced subgraph in H on this set. Also, this is called the cardinality P and the cardinality of U pillar. This is an example. This triangle is maximum. Sorry, this is maximum click. So then, if this is BB, then this subgraph is the pillar B, P, B, B, and this is 3-1 pillar. And this induced subgraph is the PBAC. And this is 3-2 pillar. Okay. And let H be a graph with smallest eigenvalue. Sorry, at least -5. Then define vectors x hat as this. So and let x bar be the orthogonal projection of x hat onto the subspace. This is the orthogonal subspace to the subspace generated by B hat. In the pillar method, first we fix a set E of rectangular lines with common angle arc cos 1/5 and base size K, and pick a graph H induced by E satisfying omega H equals K, and fix a maximum click B. Then find an upper bound on the orders of pillars P under the condition that the matrix of X bars is positive semi-definite. In this talk, I don't explain how to get an upper bound. That's not hard to do, but I can't think of a simple explanation. Okay. Next, I will write the problem in terms of graphs before going into the proof. Take a set of rectangular lines with common angle arc cos 1/5 with base size K in dimension D. Our goal is, Our goal is to show this bound. So we show if K is 5, then this holds. Okay. This can be rewritten as follows. Let H be a graph with a smallest desired eigenvalue at least -5, and omega H equals omega bracket H. And let D be the rank of SH plus 5i. Then this can be rewritten as this. If omega H equals 5, then the order of H is at the most 276 over 40 plus 10 over 3. My proof can be obtained by developing elements and sided proof for base size 6. So I describe their proof. So let H be a graph with the smallest Zeidler eigenvalue at least -5, and omega H equals omega bracket H, and D is the rank of SH plus 5i. In 1973, Lemons and Zeidler proved that if omega bracket H equals 6, then the order of H is at most 276 over 3D minus 3 over 2. And the outline of their proof is first, when the number of non-empty 60 pairs is 1, they proved this. And when the number of non-empty 3 pairs is at least 2, they proved this bound. Okay. In the proof, first fix a maximum clique over H. Then, since B is a clique, the graph matrix of B1 hat over B6 hat is 6i minus j. And this means that B1 hat over B6 hat form a regular simplex. So the sum of them equals 0. So only non-empty pillars are 6, 3 pillars. Okay. Let P be a 60 pillar. For members X and Y in P, then this in the product is if X equals Y 2, if X is adjacent to Y, then -1, otherwise 0. So the maximum eigenvalue of P is at the most 2. So P is the disjoint union of graphs, each of which is isomorphic to one of these here. These graphs has largest eigenvalue less than 2. This graph has the largest eigenvalue 2. So the number of connected components of P with the largest eigenvalue 2 is at most the order of P over 3. Okay. I use this fact. Okay. Okay. Next, I go into the proof of this. Assume only one pillar P is not empty. So, for example, this is an example. Then the order of P is the sum of the rank of 2i minus AP plus the dimension of the kernel of 2i minus AP. Then the dimension of this equals the number of connected components of P with the largest eigenvalue 2. So I use this bound. So we have this inequality. And 2i minus AP, 2i minus AP is a graph matrix of these vectors x bar. So this rank equals this dimension. So x hat is orthogonal to the subspace generated by B hat, where B is in capital B. So we have this inequality. So by this implies this inequality. Sorry. Sorry, mistake. Okay. So next, we consider the case where at least 2 non-empty pillars exist. If we can switch this pillar. As a result, we have this graph. So we can remove no-empty pillar, no-empty PB, B3, B4, B5. So we may assume that the number of non-empty pillars is at most 10. And I apply this theorem. Lemons and Zeider proved this in 1973 for, let P and B P prime be 60 pillars. Then this table falls. Okay. If P prime has an edge, then the order of P is at the most 27. Moreover, if P is isomorphic to MK2 plus NK1, then the order of VP is at most 18. K2 denotes the complete graph of order 2, and K1 is vertex. So VP is this. Okay. And if P prime has no adjacent vertices, this and this bound holds. Okay. By using this, we can derive the desired bound. The desired bound 276. For example, if every 60 pillar has edges, then we can use this bound. So the order of H equals 6 plus the sum of orders of 60 pillars, and the order of 60 pillar is at the most 27. So we derive the desired bound. Okay, this is Lemons and Zeider's proof. So, okay. Next, I explain my proof. Let H be a graph with the smallest Zeider eigenvalue at least -5, and omega H equal omega bracket H equal 5. Let D be the rank of SH plus 5i. Then I prove this. In the case where the base size 5, we should consider 2 pillar 5 1 pillars and 5 2 pillars. If there is a 5 3 pillar, then we can we switch this and this becomes 5 2 pillar. Okay, and the number of 5 pillars is 5, and the number of 5 2 pillars is 10. And 5 1 pillars have no edge, because if 5 2 pillar has an edge, then switching to vertices, then these 6 vertices form creek of order 6. Similarly, every 5 to pure have no triangle. If there is a triangle, by switching this triangle, we find creek of order 6 in switching class. Okay. Okay. For first, I focus on the 5-1 pairs. I proved that the sum of orders of 5-1 pairs is at most 5. The proof is easy. If the sum of orders of 5-1 pairs is at most 5. Sorry. It is greater than 5, then the smallest Zeidler eigenvalue is less than -5. For example, this graph has smallest Zeidler eigenvalue less than -5. So since there are edges between among 5-1 pairs, so we in this case we need to consider a few graphs. In fact, it's sufficient to verify that if the tuple of orders of 5-1 pairs is 4000 and 31000 and 22100 and 21110 after permutation, then the smallest Zeidler eigenvalue of H is less than -5. Okay. Next, we consider 5-2 pairs. Let P be a 5-2 pair. For members X and Y of P, then this inner product is 2 if X equals Y minus 1, if X is adjacent to Y, and otherwise 0. So the largest eigenvalue of P is at the most 2. Professor Lin and Professor Yu proved this bound. This holds in the case where only one 5-2 pair is non-empty. This can be proved in the similar manner. Yeah. Okay. In this slide, I explain we can embed equiangular lines with base size 5 without 5-1 pairs to lines with base size 6. For example, in this case, at the vertex B6, such that B6 hat is minus B1 hat minus minus B5 hat. Then B1, B2, B3, B4, B5, B6 form a clique of order 6. So then 5 to pillar becomes 60 pillar. So we can apply the remains and siders bound to 5 to pillars. So we can use this table. So, okay. Recall our setting and fix a maximum clique B. Then I prove this. If at least 2 5 2 pairs are not empty, then the order of H is at the most 276. Note that the order of H is the order of B plus the sum of the order of 5 1 pairs plus the sum of the order of 5 2 pairs. Now the size of B is 5, and the sum of orders of 5 1 pair is bounded by 5. So we derive this inequality. I explained that we can apply this theorem to 5 2 pairs. However, in the case where every 5 2 pairs have edges, then the order of H is bounded by 10 plus 10 times 23. It is 280. So this is greater than 276. So we should decrease this 27. This is a key corollary. Assume one of 2 conditions. First condition is that the 5 1 pair PB1 has no adjacent vertices, as in this figure. The second condition is that both 5 1 pairs PBB1 and PBB2 have at least one vertex, as in this figure. And if PBB3B4 has an edge, then the order of PBB1B2 is bounded from above by 26. Okay. I use this bound and proof. I'll give a proof of this bound. I only consider the most difficult case, namely, we assume that every 5 2 pillar has at least one edge. Case 1, we assume 5 1 pillar is of order is at least 2. So we can take 5 1 pillar of order 3 minus 2. Then we can apply this corollary. Then it is this. So, but by using the corollary, we see that these red pillars has order at most 26. Also, we use the Riemann and we use Riemann and those Seidel bound. These 5-2 pillar has order at the most 27. So the order of H is at most 5 plus 5 plus 5 times 27 plus 5 times 26. This is 276. Okay. Next, we consider the other case. Case 2, we assume every 5 1 pillar is of order at most 1. Okay. And let K be the number of non-empty 5 1 pillars. 5 1 pillars. Sorry. With that loss of generality, we may assume that PB1 PBK has order 1. If K is 1, then the order of H is at most 5 plus, this is K, 5 plus 1 plus 10 times 23. This is 276. Otherwise, I apply my bound. As a result, we obtain this inequality. So recall that this holds. So in this picture, the red pillars has order at the most 26. The other 5-2 pillar has order at the most 27. So we obtain the order of H is at most 5 plus K plus 10 minus K choose 2 times 27 and this. So this equals 275 plus K minus K choose 2. Clearly, this is at most 276. Okay. Now this is my proof. Oh, okay. Next, I explain my proof of the key corollary. I recall we recall the setting and corollary. To prove this, I prepare two claims. the first frame is this lemma. Let P and P prime be a 5-2 pillar. If P prime is non-empty, then there exists N and M such that P contains G. Okay, sorry. G, where G is isomorphic to MK1 plus MK2. And the order of G is at most 4n over 3 plus 3m. The proof is not difficult because P has largest eigenvalue at most 2. So P is the disjoint union of these graphs. And we derived the white vertices, and we can get the desired Z. Okay. So now we get this frame. In addition, the second claim is this theorem. This theorem can be proved in the same manner as Riemanns and Seidler's upper bounds. Okay, and I use the Riemanns and Seidler's bound. It is that n plus 2 times m is at most 18. I combine these inequalities. The order of P is bounded from above this value. And this can be rewritten as this. Then 2m plus n is at most 18. And now I apply this and have obtain that m is at most 8. So we see that the order of P is at most 20, is less than 27. So we derive the desired bound 26. Finally, I explain a gap in the proof by Ring and Yu. There is a unique set of 276 equiangular lines with common angle at cos 1/5 in dimension 23. In proof of the Riemann-Seidel conjecture for base size 5 by Ring and Yu, they claimed the following. Let U prime be a set of equiangular lines with common angle at cos 1/5. Then, okay, if 260, 552. Okay, so it is correct. A 60 pillar has pillars have edges, then U prime is a subset of UW. UW is this up to isometry. We found counterexample to this claim. In 2021, Grimes and others found a set UZ of 57 equiangular lines with common angle at cos 1/5 in dimension 18. This is a counterexample. Namely, UZ has 260 pillars having the edge, and UZ is not contained in UW. The proof is easy. Let SW and SG be the corresponding Zeidler matrix to them. Then the minimum norm of the lattice with graph matrix SW plus I plus 5i equals 5. And the minimum norm of the lattice with graph matrix SG plus 5i equals 4. This means that UG cannot be contained in UW. So UG is a counterexample to their claim. Thank you for your attention.